Parametric equations are just another way to represent our normal functions, but we're going to introduce another variable or another parameter to our normal equation. Most of the time up to this point, we've looked at functions where normally y was a function of x. So of course, as x changes, y changes. What this generally gave us is this gave us a two-dimensional curve in the xy plane. I just drew a parabola there kind of thing. Right, and it gave us this depiction for every x value. It gave us a y value type of picture. However, in a lot of real-world cases, the x and y coordinate of some graph actually depends on some other variable. So think about if we're talking about position. If you're talking about the position of an object, its position generally depends on a time variable. So this x and the y might depend on how much time has lapsed in a problem. So what we're going to do now, instead of y being a function of x, we're now going to define both x as some function of t, and I'm going to call it x of t, and y is also going to be some other function of t. Now t doesn't have to stand for time, and it doesn't have to be the letter t. That's just what we normally use and the easiest way to kind of think about what's happening here. So if we take a look at an example of this, we might have x is equal to t squared, y is equal to the square root of t. So now both x and y are functions of t. Now t is a brand new variable. A lot of times, it's called a parameter most of the time, and a lot of times it has a value that it runs between. Now if you're not giving any values, you'll see in a second, that just means t runs from negative infinity to positive infinity, but there's a good amount of time that t actually has a range or an interval that t goes from. So here we're going from t goes from 0 to 9. Now to sketch a curve like this, what you actually have to do is make yourself a table of values. Now this table of values actually has 3 columns because we have 3 different letters here. We have x's, y's, and t's. So if t goes from 0 to 9, just put in some values for t. I'm going to go 0, 1, how about 4, and 9. Now, you can see why I picked these is because, well, I got to take the square root of them, so I want them to be fairly decent numbers. So for the first one, if I plug 0 in for x, of course, 0 squared is 0. The square root of 0 is 0. So when time is 0, we're at the point, the xy point of 0, 0. When t is 1, t squared is 1. Square root of 1 is 1. So when t is 1, we're at, well, the point 1, 1. What did I say next? 4. So 4 squared would be 16. The square root of 4 would be 2. And of course 9, this would be 81 and 3. All right, so let's take a look at what this graph looks like. Now, since the numbers are so awful here, I'm going to have to kind of do it kind of like this. Let's go 1, 2, 3. Now, on this graph, we have an x and a y value. There's no t on this particular graph. All we're going to show is the x, y value. So our first point is 0, 0. Our next point is 1, 1. And then the next one's going to be way over here at 16, 2. And then way out here would be 81, 3. So that's 16 and 81. All right, so kind of skipping some numbers there. So if we were to connect the dots, you can kind of see that we kind of have kind of this shape here. Looks something like that. Now, we also have a mistake I just put on the board just by habit. This graph doesn't keep going here. Since t only ran from 0 to 9, the graph actually stops at that point. So let me go back and erase that arrow and put a closed circle right there. However, since the parameter has a direction, here we're saying t goes from 0 to 9, our graph now has a direction or orientation when we graph it. As we plotted the points, we went from, as z increased, we went this way, so the graph actually has an orientation. Now the way that we show the orientation on the graph is we put arrows on the curve showing the way that the graph is being sketched out or is being drawn. Now, if we didn't have any bounds here, we would assume it goes from negative infinity to positive infinity. We can still find an orientation of the curve, except for we can at the end here, if we know it kept going like that, we could put an arrow and say it goes on forever if it doesn't have bounds. But if it does have bounds, You have a starting point and an ending point of your graph. All right, let's take a look at another one real quick. What if we have x is equal to 3 cosine t, actually let's try a different, let's do theta. And y is equal to 3 sine theta. All right, now we have a different parameter here. We have a parameter of theta. It's just a letter, just like the t was just a letter. Let's go ahead and put a bound on our parameter. Let's say that theta runs from 0 to 2 pi, and see if we can sketch this curve real quick. All right, so we got to make ourselves a table. Let's do theta, x, and y. Now, since we're going from 0 to 2 pi, pick some angles that you know a lot about there. Let's go ahead and pick just our quadrant angles. Let's go 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, for each one of those, we're going to plug into here, and for the x and y value, and see what we get. So cosine of 0 is 1, so that's 3. Sine of 0 is 0. Cosine of pi over 2 is 0. Sine is 1, so that's going to be 3. Cosine of pi would be negative 3 and 0. 3 pi over 2 would be 0, negative 3. And 2 pi, well, kind of back where we started, 3, 0. So go through that, make sure that you can follow where I got all those values from. Let's go ahead and plot those real quick. Now again, when we draw these, our parameter doesn't show up in our picture. It only the dependent variables here. Let's go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So the first point that we plotted at the start of our parameter value was theta was 0. That gave us this point. 0, 3. That's the next point, and back to here. And you can kind of get the idea that this shape is probably going to be a circle, right? So let's say that it is a circle, and let's kind of draw a horrible looking circle like that. Okay, so we were thinking it's a circle, and it does have an orientation, right? That was our first point, second point, so we can kind of say that it was drawn in this orientation. All right, but from this, we could have plotted some more points to make sure that it was actually a circle, but is there another way to figure out what these graphs kind of look like? Well, to do that, we generally want to get back to our regular, kind of like rectangular equations where there's only x's and y's. So we want to eliminate this parameter. So I'm going to put this one on hold for a second. Let's take a look at how to eliminate a parameter to get back to the original curve. Or rectangular curve, let's call it. So eliminating the parameter. So let's see, our first equations we had what x was equal to t squared, y was equal to the square root of t. All right, could we actually come up with an equation for what this might be? If your parameter is just some regular t value and you just have algebraic functions like this, not trig functions, the easiest way to do it is take the easier of the two equations and solve for the letter t. Now, that's easy and hard because I said take the easier of the two. Which one's easier? Well, here's what I would say. Here, to figure out what t is, I'd have to take the square root of both sides, which means I would get a plus or minus. And that's introducing something I wouldn't want to necessarily do here. However, to solve for t here, all I'd have to do is square both sides. So notice if I square both sides here, I get y squared is equal to t. Now it's just a substitution problem. Now I know what t is. Oh, where's my red? So I can take this now and plug it into the other. So that would be x is equal to t is y squared squared. So x is equal to y to the fourth. All right, now this is a little bit backwards what we normally see. Normally we do, we solve for y. Your textbooks may do that, it may not. I would actually leave it like this, because if we solve for y, again, we're going to take the even root and we're going to get a plus or minus, so we may not want to institute that. All right, so to eliminate the parameter, most of the time when you just have algebraic expressions, take the easier of the two, kind of which one's easier, solve for the letter t and plug it into the other. Then simplify what you have. Now you may have to do quite a bit of algebra to get from what your answer is to what a book may give you as an answer, because they may have thought the other one was a little bit easier to do. Let's take a look at the one where we had trig here. If we have x is equal to 3 cosine theta and y is equal to 3 sine theta. Now when we sketched this, we kind of guessed that it was a circle. Is there any way to tell that it's a circle? Well, you actually can. To get rid of the ones where you have trig functions, we're going to use some trig identities to get rid of the trig functions. And we're almost always going to use our Pythagorean identities, like sine squared plus cosine squared is equal to 1. Or tangent squared theta plus 1 is secant squared theta. Something along these lines is the ones we're going to use. So what you normally are going to do is isolate the trig function. Get the trig function on the side all by itself. So if we do that, you can see we get x over 3 is cosine theta, and y over 3 is equal to the sine of theta. Now, since all of our Pythagorean identities have to do with the function squared, what we're going to do is we're going to square both sides here. So I get x over 3 squared, and we square this side, so it'll be cosine squared. Y over 3 squared is equal to sine squared. Now we're going to do something we've done in the past, like when we're solving systems of equations. We're just going to add two equations together. So I'm going to add these two equations together. So when I add the left-hand side, I'm going to go ahead and simplify that. I get x squared plus y squared over 9. Right? That's when I add the left sides together. When I add the right sides together, I get cosine squared plus sine squared. Well, that's what we were looking for. We were looking for one of our trig identities, one of our Pythagorean identities generally, so I can get rid of those trig functions, right? I can replace all that with a 1. So we get x squared over 9, y squared over 9 is equal to 1. Now from our conic sections, that looks like a circle. It's not quite in the form, but you can see if you multiply everything by 9, you get x squared plus y squared is equal to 9. Which is a circle centered at the origin with a radius of 3. And if you remember, our radius was right here. Remember when we drew our circle, that's exactly what we got, a circle of radius 3. So if you have trig functions involved, isolate your trig functions. Generally, you're going to square both sides, and then find the relationship between the trig functions so that you can use your Pythagorean identities. So here you're either going to add them together or subtract them, whatever it takes. All right, so eliminating the parameter does get you back to an equation that you're used to. Like we might be able to graph now x equals y to the fourth, but we have lost all direction or the orientation of the graph. Because this graph right here has no orientation, right? That's just a circle of radius 3, and that's the way that you would draw it. You need the parameterization to actually know what the original orientation was. Now, sometimes it also might be helpful to go the other way. This was eliminating the parameter, but can we actually parameterize an equation? And the answer is, yeah, we can. Now again, we're going to kind of treat this somewhat as in two categories. Generally, it's going to be a, let's go get rid of this real quick. Trig functions are kind of going to be slightly different when we're going to use those, but let's just start out with something super easy. Let's say x is equal to t cubed, I'm sorry, we're going the other way. Where we're parameterizing. Let's say y is equal to the square root of x minus 4. So this is just a rectangular equation. How do we do this? Well, if it's already solved for one letter, so here when we have it solved for y, we're kind of assuming x is the independent variable, y is the dependent variable. This is the best case scenario. All you have to do is let x be equal to the new parameter, and then plug that in, and we could see y is equal to the square root of t minus 4. So that's the best case scenario. If you have one variable solved for the other, let the independent variable be t, plug it in, and that's your second one. However, it may be kind of mixed in there. What if we had something like this? X minus 3 squared, that's horrible. 3 squared over 4, x plus 2 squared over 9 is equal to 1. Let me write that a little bit nicer. What did I say? X minus 3, something like that. All right, how would we do something like this? Well, it'd be helpful if we knew what this shape was to start with. And we know from this that this is going to give us an ellipse with a center of 3, -2. It's going to move, that's a y. What is that next? It's going to move up and down from the center 3, and it's going to move left and right from the center 2. So how could we possibly do this? Well, kind of think backwards. We said that if we had trig functions as a parameterization, like a second ago, we had 3 cosine theta and y is equal to 3 sine theta. This gave us our circle in this case with a center at 0. And what did we do? We took this and we solved for the trig functions, and then we squared both sides. So what would happen here? How could we actually do that? Well, notice we have something squared on each side, and we have something squared plus something squared equals 1. Well, I'm thinking that's probably the same type of identity, right? Sine squared plus cosine squared is equal to 1. So how could we do that? What about this? Let's clear our fractions here real quick. If we clear our fractions, I'd say we multiply through by 36. So I'd have 9 times x minus 3 squared plus 4 times y plus 2 squared is equal to 36. All right, that skip is the reason that you put your phone on airplane mode when you're recording videos. So where were we? We were trying to make a substitution here to get into a new parameter for what x should be and what y should be to make this true. Now here we multiplied through by 36, which isn't a bad idea, but now that I look at it, it may have been easier to leave it like this. Remember, we're aiming for one of our trig identities. Now the reason I said leave it like this is because we already got the 1 on that side. We know that this is true. We know that cosine squared theta plus sine squared theta is equal to 1. So what would my substitution have to be up here to get me to this? Well, if I let's see if this would work, see if this makes sense. I know cosine has to be squared, so I know the thing in there needs to be a cosine. So if I just let cosine theta be equal to x minus 3, and I plug that in, that would give me cosine squared over 4. But I don't want the 4 to be there either. So think about it like this. If I made that 2 cosine theta, when I squared 2 cosine theta, I would get 4 cosine squared over 4. The 4's would cancel. So if I do the same thing over here, if I let, let's say, because I want the 9's to cancel, I want the sine of theta to be equal to y plus 2, but I'm going to need a 3 out front so that cancels. That substitution should work. Now I'm going to leave some room because we still need to solve for x and y here. So you notice if I plug that in, if I say 2 cosine theta equals x minus 3, that's 2 cosine theta squared over 4 plus 3 sine theta squared over 9. Does that equal to 1? Well, that's 4 cosine squared theta over 4. 9 sine squared theta over 9. So that's cosine squared theta plus sine squared theta is equal to 1. So that substitution should work if we do this. So now all I got to do to actually get to my parameterization, let's solve for x. So x is going to be equal to 2 cosine theta plus 3, and y is equal to 3 sine theta minus 2. Okay, so you can see when we're doing the trig substitutions, it's a little bit more difficult. You just think about what we did over here, just kind of doing it backwards. You want to come up with a trig identity that's true. Like I said, I probably shouldn't have cleared the fractions because it's easier to see when you actually have a 1 right there. Okay, so there we go. There's our parameterization for this. I'm going to get kind of showing that it did work out of the way. So parameterizing a curve can be helpful. Now we have the x's and y's in terms of a brand new variable theta, which we can use just like any other parameter. Now, in real life, we may actually want to put bounds on what we think theta should be, right? Theta should probably go from something like 0 to 2 pi, depending on what our circumstances are there.